Okay, so in the last couple of videos we've been talking about relations, functions, domain, range, and obviously the various set notations that we need to be able to communicate about those things. Today we want to have a look at how we can categorize relations. So we've already looked at the fact that some relations are functions, but we want to break that categorization down a little bit further as well. So essentially, all relations can be divided into one of four categories, okay? Either one-to-one, many-to-one, one-to-many, or many-to-many. Okay, so when we talk about, essentially, when we look at the something to something, we're talking about input to output, okay? So when we talk about a one-to-one function, it means that for every one piece of input, one x value, there is one unique y value, okay? And so an example of something, a function where that happens is, and vice versa as well. For every one y value, there is one unique x value. So an example of a function where that would happen would be in the function y equals x cubed. Okay, not true for all cubics, so we can't be too general about that. If I have a cubic that looks like this, that is not a one-to-one function, okay, because there would be this 1x value here produces this 1y value here, but this other x value over here also maps to this 1y value here. And so this would be an example of more than one x value, many x values can produce one y value, okay? So not all cubics, but the y equals x cubed. Other functions which might be one-to-one, linear function. All straight lines will be one-to-one. Any x value produces just one y value, and vice versa. That y value is only connected to that one x value on the line. Okay. Square root graph. Every x value maps to just one y value, and vice versa. You know, this one y value here, there's only one x value that corresponds to that. So it's a one-to-one function. Other function types we've looked at, hyperbola. Hyperbola is also a one-to-one function. Oops, sorry. This 1x value here produces this 1y value here. Similarly, this 1y value here only produces 1x value. That y value is only connected with 1x value. Similarly, this 1y value down here only connected with the 1x value, and vice versa. So a hyperbola is also a one-to-one function. The next categorization is many-to-one. And that's where many pieces of input, many x values, could produce the same one y value. Okay, so again, many doesn't mean lots and lots, it just means more than one. So, for example, a parabola is an example of a many-to-one function. More than one x value, these two x values here, both map to or produce the same y value. Okay, so many x values can produce the same one y value. What would be another many-to-one function? Something like, well, we talked about that cubic I drew before. A truncus would be an example of a many-to-one function. More than one x value produce the same one y value. Okay, but for every, so any one y value maps to more than one x value. Okay, so we've got that connection. So a truncus. What else have we looked at? So as I said, some cubics that do something like this, they would be many-to-one. What else have we looked at? Something like a semicircle. It's a bit like a parabola in shape, only upside down. Same idea. Many x values producing one y value. Truncus, hyperbola, that's probably most of the graphs we've looked at. Right, then we have one-to-many. In a one-to-many relation, any one x value, one input value, could produce more than one y value. So for example, this is a function we haven't really looked at, but this is actually, well, this would be the positive square root of x, and this would be the negative square root of x. If we put those together, we've got y equals positive or negative square root of x, which means that y squared is equal to x. So it's essentially, so this is the rule, and that's the full sideways parabola, not just half the sideways parabola. And when we draw that graph, it is a one-to-many function. This one x value here can result in more than one or many y values. Okay. We haven't really met a lot of those sorts of things yet. We haven't even really technically met that one, but that's the most obvious example closest to what we've already talked about. And the fourth category of relation is a many-to-many relation, and the circle is the most obvious example of that. And that is where more than one x value can produce more than one y value. So this x value over here produces two y values here. This x value over here also produces those same two y values. There are many x values that could map to many y values. Okay, so a circle, circles are really the only example of many-to-many functions that we've looked at. So which of the following could also be functions? So clearly many-to-many, not a function, failing our vertical line test. One-to-many, also not a function. The issue is the many. Those are going to have x coordinates, whether 1 or 2 x coordinates, that have different y coordinates. So for example, the 1x coordinate could have different y coordinates. So therefore, failing our no 2 points with the same x coordinate rule to do with functions. Okay, so those two are not functions. These two, many to one, these are functions, and these are functions. Again, it's about the one here. Whatever the x value is, whether it's the same or different, it's producing only the one y value, and so therefore there's only 1 point on the graph with that particular x value. So one-to-one and many-to-one are functions. Okay, so last lesson we talked about how some relations are functions, and then we can now define those functions even further as being either one-to-one functions or many-to-one functions. All right, let's talk specifically about one-to-one functions and how to identify them, because that's an important skill when we get a little later on in this chapter and we talk about inverse functions. We need to be able to identify a one-to-one function before we can think about its inverse. We'll talk more about that later on. So when we want to decide if a relation is a function, we use the vertical line test, because that allows us to test that if we have a function, we're only going to hit the graph once. Okay, we're only going to have, so there'll be no 2x coordinate, no 2 points with the same x coordinate. When we want to test if it's a one-to-one function, we also want to know if there are no 2 points with the same x coordinate. So the cubic, for example, we also want to know that there are no points with the same, no 2 points with the same x coordinate. Yeah, so this point has this x coordinate. There isn't anywhere else over here, for example, with the same x coordinate, because that would make it a many-to-one function, not a one-to-one function. So we're looking for horizontal lines to see whether it is so vertical line will tell us it's a function, then horizontal line will tell us whether or not it is a one-to-one function. And if it's not a one-to-one function, it must be a many-to-one function. So this cubic I've drawn here, for example, is not a one-to-one function because there are many x values that have the same one y value. It's a many-to-one function. Okay, so which of the following functions are one-to-one? So it's a function because it passes vertical line. It's a one-to-one function because it passes horizontal line. So this one, part A, is a one-to-one function. Part B, it's a function because it passes vertical line test. It is not a one-to-one function because it fails horizontal line test. So this is a many-to-one function. So not a one-to-one function. The truncus, again, passes vertical line test, so it is a function. Fails horizontal line test, so it is not a one-to-one function. Therefore, it must be many-to-one. This cubic with the point of inflection here, that's a function. It's also going to pass horizontal line test. Even at that point there, we have a moment of zero gradient where the line's going to cut through the graph, but it doesn't, it's not a very clear graph, but the graph doesn't get completely flat for a long period there. It's just flat at that one instant, and after that we've got, so if we were to imagine zooming in, it's going to be still very, very slightly sloped, moment of zero gradient, then it starts to slope the other way, so we're still going to pass our horizontal line test. Okay, so this one is a 1-to-1 function. So therefore, A and D are 1-to-1 functions. Okay, then we want to talk about the idea of an implied or a maximal domain, and we've touched on this a little bit before now. So if the rule of a relation is given with no specific domain, or a function with no specific domain, then its domain is assumed to be the largest possible set of x values for which that relation or function exists, and we call that the implied or the maximal domain. All polynomial functions, linear, quadratic, cubic, etc., have an implied domain of R. Okay, there's no restriction whatsoever on what you can put into those equations. If you've got a polynomial equation, let's say, y equals x cubed plus 5x squared minus 2x plus 1, you can put any x value in here and calculate a y value. It could be enormous, it could be small, it could be decimal, it could be fraction. You could put pi in there. Pi cubed plus 5 pi minus 2 pi plus 1. That's the y value, okay? There's no restrictions whatsoever to what you can put into a polynomial function. Thinking graphically about them as well, they exist for all real numbers. Lines, parabolas, cubics, okay, quartics, we could go on and on. Of the relations we've dealt with so far, there are two main features, algebraic features that we see in equations that mean that those relations do not have implied domains of R. And they are equations involving square roots, which we'll talk about first, and then equations involving fractions, which we'll talk about. It doesn't just have to be a square root, it could be any even root, so 4th root, 6th root, 8th root, okay? Let's stick with the square root for now though. The reason we get a restriction when we have a function involving a square root is because it's not possible to take the square root of a negative value, okay? So square root of -5 is undefined. It does not exist in the real number system, and we're only dealing in the real number system. So therefore, if we have a square root in our equation, whatever is underneath the square root has to be positive for that function to exist, okay? So for example, if our equation is y equals the square root of x, we know that whatever goes under here doesn't just have to be positive, it can equal 0, square root of 0 is 0, but it has to be bigger than or equal to 0. So x has to be bigger than or equal to 0 for that to exist, and so therefore we can say that our domain would have to be from 0 to infinity. In part B, whatever's under the square root, so in this instance, that is x plus 3, is going to have to be bigger than or equal to 0. And so that means that x has to be bigger than or equal to -3. And so therefore, the implied domain of this function is going to be from -3 up to infinity. This function here, again, whatever's under the square root, the only way this function will exist is if that is bigger than or equal to 0. So we can solve that. We can add x to both sides, which means that x is, less than or equal to 6. And so therefore, the implied domain of this function is from -infinity up to 6. If you think about your transformations for this, okay, this is negative x minus 6, reflection in the y-axis, and then to the right by 6. Your graph looks like that. It matches with the fact that this is its domain. Okay, same thing here. This is translating that square root graph to the left by 3. So it's over here. So it makes sense that domain is -3 to infinity. But equally, those two things work together. So equally, the domain is -3 to infinity because algebraically that's the only thing that makes sense. Okay, so sometimes if you're having trouble sketching your graph or thinking about your transformations and what's happening, think about the domain first. Okay, this helps you thinking about in part E and C in particular, knowing that the domain is from -infinity to 6 really helps you to think about that shape and, oh, there has to have been a reflection in the y-axis for that to happen, and the endpoint must be at 6, etc., etc. Right, then we have this one, square root of x squared minus 4. Okay, so this isn't a square root function. This isn't and this is where we want to think about, I don't know how to draw this. This isn't 4 minus x, square root of 4 minus x squared, which would be the circle. This isn't either of those things. So I need to be able to think algebraically about the domain of this. The square root is the only thing that's restricting what x could be. It means that whatever's underneath it has to be bigger than or equal to 0. Now here we have a quadratic inequality, a non-linear inequality. And there's only one step for solving those. thinking about a graph. So this is asking me, when is the graph of y equals x squared minus 4 bigger than or equal to the graph of y equals 0, i.e. on or above the x-axis? So x squared minus 4 is a parabola translated down by 4. The x-intercepts are positive 2 and negative 2. So this is the graph of x squared minus 4. This is y equals 0. When is that bigger than or equal to that? At those 2 points and here. So for x values, where x is bigger than or equal to 2, or where x is less than or equal to negative 2. So x less than or equal to negative 2, or x bigger than or equal to 2. So that means our domain is from negative infinity up to negative 2, including negative 2, or, so union, from 2 up to infinity. Okay, as I said, the other algebraic restriction that means that our domain won't be R is if we have fractions. And by that I mean fractions where the unknown is in the denominator. And that's because it's not possible to divide by 0. So that means that if you've got a function, whatever is in the denominator of that function cannot be 0. So in this particular function, we know that this won't exist if x equals 0. So x could be anything except for 0, which means that the domain is going to be all the real numbers except for 0. Here, we've got a fraction. This will exist as long as that denominator doesn't equal 0. And that will happen if x equals 7 on 2 or 3.5. Okay, so x can be anything except for 7 on 2, because 7 on 2 is the one number that would make that denominator 0. So the domain for this particular function, any real number except for 7 over 2. Okay, part C. This graph will exist as long as that denominator doesn't equal 0. So x plus 1 times x minus 5 cannot equal 0. Now again, here I'm getting into territory of this is a graph that I don't know what it looks like. These two graphs you might have been able to think about drawing them to think about the domain. Here, this is something different that we haven't dealt with. Okay, we've got a quadratic expression on the denominator. It's not all squared. It's not just a truncus. There's a bit going on here. But we can think algebraically about the domain. We know that whatever's on the denominator of that fraction cannot equal 0, which means that x cannot equal negative 1 and x cannot equal positive 5. Okay, and so therefore the domain of this function, but otherwise anything else would be okay, because then the denominator won't be 0, and therefore we can do 1 divided by anything that isn't 0. So the domain here could be any real number except for these two numbers. So we want to list them in as a set, not as an interval, so we need the curly brackets. So the domain is all the real numbers except for the numbers negative 1 and positive 5. Alright, then part D, again, it's only about the denominator. Doesn't matter what's happening up here. X can be anything. 2x plus 3 can equal anything. You can have 0 on the numerator of a fraction. You can have a positive number. You can have a negative number. You can have a fraction. You can have a decimal. It's only impossible if the denominator equals 0. So x plus 4 can't be 0, and so x can't be equal to negative 4. And so therefore the domain, any real number except for negative 4. Okay, so sometimes we might combine those two things together. Combinations of even roots, so square roots, fourth roots, sixth roots, etc., and fractions. So state the implied domain of the following relation. Okay, so let's think about, first of all, the square root means that 5x minus x squared has to be bigger than or equal to 0 for the square root to exist. But if it were to equal 0, the square root of 0 is 0, and then the denominator of the fraction would be 0, and that would be a problem. So in this instance, we need 5x minus x squared to be bigger than 0. Now again, we have a quadratic inequality. Okay, this is a sad parabola with intercepts at 0 and 5. So it looks something like this. Okay, that's y equals, sorry, that's 5 there. That's y equals 5x minus x squared. This is y equals 0. We want to know where the quadratic is bigger than the x-axis, y equals 0. And that happens not at these points, because that's when it will equal 0, but anywhere here. So x values that are between 0 and 5. Okay, so the domain for this particular function, 0 to 5, not including 0, because that would make 5x minus x squared 0, which would make the denominator of the fraction 0. Also can't equal 5, because that would also make 5x minus x squared equal to 0, and therefore the denominator of the fraction would be 0. But it can be anything in between there, because that's going to produce a positive number under the square root in the denominator of the fraction. Okay, work today is exercise 5D, having a little think about one-to-one, many-to-one, etc. kind of functions, and also calculating implied domains.